I say reluctantly because the tone of the letter is reluctant. They didn't want to do it, but they have to. They treat Bitcoin as a non-security commodity, which is great after all the claims of Bitcoin is the new gold. It seems appropriate, but it also comes with extensive tax implications that needs to be enforced. The SEC also mentioned that Bitcoin is used for illicit activity, and they mention Chainalysis by name, and they say something like, okay, it is used for illicit activity, but at least we know that it is used for illicit activity. So they gain some comfort just by having this ability to analyze the Bitcoin graph. Okay. So the result of this is now Bitcoin is tightly integrated into the existing financial system. On the other hand, we have mechanisms like crypto mixers, a fully opaque mechanism, a fully opaque system that an external viewer cannot look inside and cannot see the transactions. So on the other hand, we saw the government ban one of these mechanisms not too long ago. And the interesting thing is that in order to ban this mechanism, the government doesn't need to do blockchain operations. It doesn't need to do anything with the blockchain. For the government to ban something, it just needs to put some addresses into its own list, and the mechanism is effectively banned. So long talks about censorship resistance. It doesn't matter if you have, if the system has mathematical properties of censorship resistance. In practice, it doesn't matter. Another interesting fact, after this announcement, some of the major actors are overcomplied. Overcomplied in the sense that they banned other addresses that they themselves deduce that was in touch with the suspected addresses. So what we see is a willingness to comply. The actors want to comply. They need the tools to do it. So we see that fully opaque mechanism doesn't work, and we see that fully transparent mechanism doesn't work. We need to create something in the middle, either add compliance to a fully opaque system or add privacy to a fully transparent system. Let's talk for a second about the B2B use case for public blockchain. So currently it's not being used, and the reason is because privacy is required for this use case. We cannot have a company publishes its entire business expense to the public ledger. It doesn't make any sense. Privacy is a minimum requirement for the B2B use case, but also compliance. Company needs to comply with the law. It needs to pay taxes. There has to be a way to demonstrate that the company's activities are done according to the law. And as far as we know, there is no such system that provides this entire set of features. So we have our motivation for compliance. So there are multiple approaches that we can take in order to provide compliance. We can take a fully opaque system and provide enhanced viewing keys. We can try to enforce blacklist, whitelist. We can add traceability. We can play with privacy budgets. There are other methods as well. Today we are going to focus on one specific method and see some proposals on enhanced viewing keys. We will focus on a specific system. So we will look at Zcash. So Zcash is a fully opaque system. It provides complete privacy. It uses a lot of cryptography to achieve this goal. And it already has a viewing key mechanism. So the existing viewing key, it provides the ability to disclose my transaction history. it is separate from the spending key, meaning I can provide my viewing key without the need to provide my spending key. Whoever has the viewing key cannot spend on my behalf. The viewing key will reveal my entire history, and the revealed addresses will be the re-randomized addresses. So it doesn't necessarily help us with linkability. And one more thing, the viewing keys on Zcash is not enforced by the consensus, meaning I'm as a user, I can put some garbage in the fields and then give my viewing key, and the other party will be convinced that I didn't do any transactions, while in fact I simply didn't report them to the viewing key mechanism. Okay, so we are currently working on a proposal, something that we call enhanced viewing keys. This is a work in progress. The details are not finalized. Everything is subject to change. So let's see it. So we're building the enhanced viewing keys on top of Orchard ZSA. Orchard ZSA is an extension of the Orchard protocol. In addition to regular Zcash functionality, it allows you to issue and transfer newly created assets in a permissionless way. So the ZSA extension, so the Orchard protocol is a node-based protocol. It has nodes. These nodes has a lot of properties, addresses, values, and the ZSA extension adds another property to the Orchard protocol, which is the asset base. It's basically a different way to say asset type. We didn't use the word type because it's ambiguous. So asset base, it what defines the type of the asset. To derive the asset base, we hash together the identity of the issuer and some generic description. The description is defined by the issuer. The issuer can put basically any string according to its business logic. We hash everything together. We project it to a group, and we get our asset base, which is in the Orchard case elliptic curve base point. And this is how we derive the asset base. The asset base is an addition to the existing node properties. Okay. So in Orchard ZSA, this is an action. An action is a data structure that binds together the node that is being spanned with the new node that is being created. So in order to provide a valid Orchard ZSA action, some of the public values that need to be provided are the nullifier. The nullifier is basically a publicly known identifier for the spent node. Then we need to provide the node commitment for the new node, and we need to provide a proof that all the computations are done correctly. In addition to this, the new node is not revealed to the public. It is encrypted, and it is sent to the recipient in its encrypted form, again, using the blockchain. The encrypted node is not being verified by the consensus. This is not so bad because if we try to cheat this mechanism and instead of providing the actual node, we will provide some garbage, this is basically the equivalent of burning money. So there are plenty of ways to burn money. This is another way to burn money. We are not concerned with this. This is not a rational behavior. So the fact that this encrypted node is not verified, it's not that bad. What we would like to do with enhanced viewing keys is to add another field with some encrypted information for an auditor to every single action that the the protocol produces. And we want to require that this additional field, even though it is encrypted, we want to have this field verified by the consensus. In order for legitimate users or any type of user not to be able to cheat the system. So we want to verify this by the consensus. Okay, so we need to decide what is the plain text for this additional field. So the suggested plain text is to have the diversified address of the spent node. This is the old, what we see on the left. In addition, we will have the diversified address of the newly created node. And we would like to have the value of this transaction. Okay, what we are getting of this? We are getting the ability to build these graphs, these Bitcoin style, to do this Bitcoin style graph analysis. Basically, whoever has all these plain texts, the auditor, can create a graph and link the financial activity all the way back to issuance. Basically, the auditor will get to see the same picture that any one of us can see while analyzing the Bitcoin transaction graph. What is important to understand here that this is not some kind of master key mechanism to reveal the entire Zcash blockchain activity. This is a mechanism to show the graph only for this specific asset type, only to this specific auditor. So we have multiple auditors, multiple asset types, some of them audited, some of them not audited. Everything is mixed together. And we will be getting, the auditor will be getting this information. Okay, so let's talk about the verified part. First of all, we need to show that the plain text is constructed correctly. So in order to show that the plain text is constructed correctly, we need to tie the diversifier of the spent node to the nullifier that is publicly known, and we will be tying them together using the secret values of nullifier keys, the commitment, and others. I will omit some of the complexity in the following slides. We also need to show that there is a proper connection between the commitment of the newly created node to the diversified address that is part of the plain text. And we will do the same for the value. Or we concatenate everything together and show the proper relation with the nullifier, the commitment, and other witness values. Okay. Next, we need to show that the ciphertext is constructed correctly. So we have the ciphertext. We want to demonstrate that indeed the encrypted plaintext is as expected. And we need to show that it was encrypted to the correct auditor using the correct key. This statement is a bit vague. In order to make it more concrete, we need to introduce some more machinery. So currently for Orsha ZSA, we have the issuance keys, one secret key for the issuer and one public key for the issuer. The secret key is used to sign a new issuance, and the public key is used to verify that this issuance process is done correctly. We need to have another set of keys for the auditor, one secret key for the auditor, and one public key for the auditor. Either they will be derived in a direct relation to the issuer's key, or they can be also independent, meaning we can have a use case where the issuer is not the auditor. The issuer can still remain in the dark about the transaction information, but the auditor will have this visibility in this use case. So we've seen that asset base is derived by concatenating the issuer's public key and the asset description, then projecting to a group. Now we add the identity of the auditor into the asset base. Basically, in some sense, we bake the auditor into the asset type. Okay, now we have the necessary parts to go back here and to say something like the encrypted ciphertext has the proper relation with the commitment of the new node. And some of the values that help us to prove this statement is the newly defined asset base and the public key of the auditor. They are marked in blue because we don't want to disclose neither the asset base nor the identity of the author. We want that no one would be able to distinguish between this auditor and that auditor, and audited assets and not audited assets. So these values are part of the witness and are not publicly available. Here we present asymmetric encryption, but we can also replace it with symmetric encryption at the cost. And the cost is we need another step of key exchange, similar to what currently is being done with the encrypted nodes. And in addition, we need to prove that this process of key exchange was done correctly. So bigger proof. This is work in progress, and we have some challenges. One of the challenges, the encryption scheme should be quantum secure. The requirement for Zcash is to have quantum secure privacy, meaning that any encryption scheme that we choose, it has to be quantum secure. A lot of encryption schemes are off the table. We did a pilot of verifiable encryption using Halo 2. You can have a look, but the encryption that we used there was Al-Gamal encryption, which is not quantum secure. It is easy to model, but it doesn't meet the requirements. The next challenge is we need to model the encryption scheme as a circuit, as a zero-knowledge circuit, something that I expect to be a significant effort, no matter which quantum secure encryption scheme we would choose. We also look on verifiable encryption schemes where the encryption is not part of the circuit. So maybe there is a way to exclude the encryption out of the circuit. We are not sure yet. We are looking into this. But what is sure that systems such as Halo 2 that are very general, we can model the encryption using such a system. Okay, some open questions. We don't know yet the proof size, the proof generation time. We didn't even choose the encryption yet, so it's an open question. Another open question is, does this additional proof needs to be part of the existing orchard transfer proof, or it should be completely independent proof? So the gain by combining them both is that the orchard transfer proof is already computing the commitment. So we gain some efficiency gain by reusing this value. On the other side, if these are two different proofs, we get modularity, better modularity. It's an open question. Another question is, do we require indistinguishability from regular transfers? So there is a significant cost to this. If regular and compliant transactions look the same, it means that regular transactions need to be inflated in the same amount of information, and to look like a compliant transactions, this will have a significant blockchain space cost. So at least here I'm leaning towards no. But again, this is open. And if the answer is no, do we create a separate pool for compliant assets? So we can have the existing pools for Zcash to behave exactly the same as they behaving today, and to have another pool which is completely isolated. I say isolated because right now the value can flow between the pools. We can move value between transparent and sapling and orchard and back. So this new compliant pool, in order for all of this to make sense, it needs to be isolated. It can be isolated, work on the side, keep every single privacy guarantee that Zcash already provides, continue to provide these privacy guarantees, work on the side, still being operated on the same blockchain, but isolated from the rest of the pool. Some appeal in this proposal is that for potential actors, it will be much easier to convince them to onboard into this model, because we just need to show the new functionality and to show that it is impossible to move value between the compliant pool to the other pool, instead of selling the entire property of the Zcash blockchain. It's an easier sell, because if you give someone the Zcash spec and tell them try to audit the spec, it's a hard task. It's a hard task for the industry. It's a hard task for everyone. So it's a smaller amount of things to audit. I think we can conclude with this. We have time for some questions, please.
Thank you for the presentation. I have one question regarding the design decision of putting the encrypted data on-chain. So I feel that you're basically replicating encrypted data that is really only meant for one recipient, which puts additional storage requirements, plus gives you the problems regarding quantum security and indistinguishability. Why wouldn't you opt for a design in which you basically, if you do a transaction, you send the data to the intended auditor, you get a receipt from the auditor, and then you prove knowledge of a receipt as received from the auditor that basically they got all the data they need. I feel that this could solve some of the challenges you're encountering.
Yes, we consider this approach, but it creates an interactive protocol with the auditor, basically with multiple auditors. If we go with this approach, which is also being considered, but then it's not self-contained. We need to do interactive protocol. What happens if the auditor gone offline all of a sudden, if the auditor disappears? Like here, it's like you done your thing and you forget about it. It's up to the auditor to get the data. In your suggestion, the auditor needs to be live all the time, have a server, functioning server, always send request, reply. He can tamper with the blockchain in a way, like he can simply disappear, and then we don't know how to behave. Yes, but you have a blockchain interaction that you need to take care of, right? All of a sudden, your blockchain is dependent on auditor action that might not be as expected. You need to deal with all these edge cases that are not so simple.
We have a question there.
Hi, I'm going to ask this question with a US framing because I think it makes the problem particularly stark, but it's intended more globally than that. So one issue with kind of techno-solutionistic approaches to law and policy issues like this, is that you can spend a ton of resources on research and engineering and lobbying and come up with some great solution, and then like forget John Roberts and Gary Gensler, like 3 random Fifth Circuit, court judges or a data privacy regulator in Maryland can basically say throw this all away with you having like very, very little recourse. And so I guess my question is, how viable do you think it is to develop techniques like this that would work not just for like one particular regulatory regime, but be designed to be responsive to changes triggered by new legislation, new case law, or like new administrative rulemaking?
So this is not a technical question. So we can see that, that the US, in some sense, the regulatory framework for the US is some kind of a guideline for many countries. What is allowed in the US, allowed many times post-fact in many countries, and the opposite. We see that the US government is satisfied enough with the ability to inspect the Bitcoin blockchain enough to make it an ETF. So this is our closest approximation to how we understand could work for the regulatory environment.
Hi. I want to make clear that I'm completely opposed to this. What do you do about the objection I made before when I was on the panel that auditor keys will leak?
Can you repeat the entire question, please?
So what's your response to my assertion that auditor keys will leak?
Yes, auditor keys might leak, but in the current financial system, the audit keys for banks can also leak, right? So we need to protect them. We can introduce another set of cryptographic tools, such as distribute the auditor key. We can distribute it to many parties. We can take precautions, the same precautions that are taken today in the current financial system. This is the best we can do.
It's not the best you can do. So in the current financial system, those bank-to-bank communications are over sort of a private network. Whereas this is on a public blockchain, the ciphertext is there forever for anyone to download. I mean, that's not the only problem. One of my other concerns, apart from efficiency, is over-compliance. So that this, for the traced assets, it makes them essentially as transparent as Bitcoin. Has any regulator actually asked for that?
So the answer is no, because the system is not existing. It's a chicken and egg problem, this is for sure. But we did see in the case of fully opaque systems getting banned, and this is what we are trying to prevent here.
Let's thank the speaker one more time. Thank you, Pablo.
Thank you.
Okay, so we're going to go for a coffee break. Before you go, I know that we've taken you 13 minutes off of that. I just want to remind you all that after the next session, which is another about 2 hours,